Good evening. Am I audible, Nasim?
Yes, yes, you are audible.
Okay. Screen is visible, right?
Yeah, yeah, screen is also visible.
So, good evening. Welcome to the 11th live session of this course, Numerical Methods for Engineers. Last class, we had started discussing about ordinary differential equations, the different numerical techniques to solve the ordinary differential equations based on the techniques which we have learned during numerical differentiation, then numerical integration. All those techniques we were using here. So in the last class, we had discussed about the different techniques of solving a numerical ordinary differential equation numerically, like we had the Runge-Kutta order 2 and order 4 method. Then we had the Euler's method, and then we solved some problems on the different techniques. Today, what we will be looking into, the same topic we'll be looking into for the next two classes. So today we will be taking up the error analysis. That is, what is the order of the error, how you can find the error in the different methods or the different numerical techniques which we had discussed last class. Then we first will look into that, the error analysis in the Euler's method, the second order RK method, fourth order RK method. Then we'll be moving to stability analysis of the different numerical techniques, whether what is the optimum choice for the parameters like the step size and all, so that our so that our numerical method is stable and there are no oscillating solutions. And then we'll look into one more technique which is new little bit, but using the existing techniques only. So that is known as the predictor corrector method. So these three topics we will be looking into today. And so let's get started. Error analysis in RK method. So first we'll look into error analysis in the Runge-Kutta method. I'm audible, right?
Yeah, yeah, you are audible.
So first we'll look into the error analysis in RK method. Then we will look into RK2. First we'll look into RK2 method. Then we'll move to the Richardson's extrapolation. And then we will see the stability and this one error order of Euler's method. Okay. Okay. So let us consider a differential equation. Consider a differential equation. So this is for a circuit equation. A series RL circuit is present, and that is given by the circuit is basically given by the model of the circuit is di by dt equals to v by L minus IR by L. And the initial condition is given as I of 0 is 0. And these parameters are given L equal to 2, R equal to 4, and your V is given as 5 volts. V is 5. Okay. So for this, we need to first solve this equation. We can solve it analytically also. First, we'll solve it analytically. We'll find what is the true solution. Then we'll compare the different numerical techniques we will be using, and we will be comparing the errors in the different numerical techniques. So is it clear what we are going to do?
Yes, yeah, I am clear. But I understood the problem.
Okay. Okay. So if we just recall what is RK2 method. In RK2 method, the iterating equation is yi plus 1 equal to yi plus h by 2 into k1 plus k2. What is k1? K1 is the slope of the function at xi yi, and your k2 is the slope of the function at xi plus h yi plus hk1. So these three equations you need to remember for your RK2. Okay. So first we will solve it analytically. Okay. No RK2, RK4, nothing. Just we'll solve it analytically. So please, one second. What is the given equation? Di by dt equals to V by L I into R. So we can, this V by L and R by L, these are constants, right? So we can simplify this equation like alpha minus beta I, where your alpha is V by L and your beta is R by L. Is it clear? We have just replaced the constants because those constants will be difficult to handle in the course of the equation. So we have basically replaced that by alpha and beta. Okay. So now we need to solve this equation. So we bring this alpha minus beta I to the denominator and here. Now if we integrate both sides, what will be the integration on the left hand side? Can you tell me?
It will be natural log of alpha minus beta I.
And one more term will come minus 1 by beta.
Yes, yes, yeah, the differential upon
Alpha
minus 1 by
minus
beta
beta. T
equal to t
plus
plus c.
C. So your initial condition is given I of 0 is 0. So I think this will be minus 1 by 4. Now, so if we substitute using the initial condition, we can find the value of C. Using initial condition, if we substitute, C will be equal to minus ln alpha by beta, right? Because I of 0 is 0. So now we can rewrite the solution as minus 1 by beta or minus beta I equal to t minus beta. So this is your solution, right? So now we need to find out in terms of I, right? So we need to make I equals to something we have to do. So we can write ln alpha by beta minus ln alpha minus beta I by beta equals to. So 1 by beta if we take common minus so ln a minus b is ln a by b, right? Equals to beta t. So alpha by, if we want to remove this logarithm, get e to the power beta t, right? From this we need to find out I. If you find out I from here, you will get so this will be your I. I will be equals to alpha by beta 1 minus e to the power minus beta t. So this is your actual solution obtained by analytical techniques, right? Is it clear? How did I solve this? The integration part is clear.
Yes, yes, it's clear.
Okay. So now we need to substitute this alpha and beta, right? So your alpha is V by L. So it is 5 by 2 2.5. And your beta is how much? Beta is R by L. R is 4, L is 2. R by L. 4 by 2 equals to. So if you substitute this, your solution will be alpha by beta. So it is 1.25, 1 minus e to the power minus 2. So this is your solution. Correct? This is your actual solution. So now we have to find out the uh, the true value. At what point we need to find out. So here we will be finding out the true value of the function at 0.2. T equals to 0.2. Okay. So it is 1.25 minus e to the power minus 2t, right? So it is minus 0. So if you substitute here, you will get 0.4120. So this is your true value at 0.2. Now we'll solve it numerically using different step sizes and we'll see what is the order of the error. Okay. Now we will solve by RK2. So in RK2, first we have to find out. Okay, first we need to see what H value we will take. So first we'll do with H equal to 0.2. So in one step only we will get the solution, right? Because H is 0.2 and you want to find the value of the function at 0.2 only. So initial value is 0, then you have 0 plus 0.2. In the next step only we will get only one iteration we need to do. So what is K1? K1 is f of xi comma yi. So it is basically f of 0. Now remember what is f? The slope of the function, not the value of the function. Okay. So what is the slope of the function? V by L minus R by I R by L. So if you substitute 0, 0 here, you will get V by L only. So what is V by L? V by L is 5 by 2. It is 2.4. This is K1. What is K2? K2 is f of xi plus h and yi plus hk1. So xi is 0, 0 plus h is 0.2, 0.2, comma y of 0.2. That is I of 0.2 plus h is 0.2, k1 is 2.5. Sorry. I of 0 plus 0.2 into 0.5. F of 0.2 comma I of 0 is 0, 0 plus 0.2 into 2.5. 2.5 into 0.2 is 0.5, right? So it is f of 0.2 comma 0.5. So it is V by L minus 0.5 R by L. V by L is 2.5 minus 0.5 into 0.5 into R by R is 4, L is 2. 2.5 minus 0.5 into 2 is 1.5. K you have, K1 you have, K2 you have. Now you can find out Y of first step. That is Y of 0.2, 0 plus H by 2. Y of 0 is 0. H is 0.2 by 2. 2.5 plus 1. So it is coming out to be 0.4. So your I of 0.2 using RK2 method and using step size of 0.2, it is coming out to be 0.4. What was your I true? I true was 0.4120. Now if you find out the error is 0.4 minus 0.4120 by 0.4120. So it is 0.012. 2 point. You have an error of 2.91%. Is this clear? The entire step, the
Yes.
steps are clear, or should I explain it once again?
No, the steps are clear.
Okay. So now you can see here, we used a step size of 0.2. That is, we got our solution in one step only. Had we used smaller value of h or step size, then we would have taken larger number of steps. But our solution would have been more accurate then. So that we will be showing here. Just you see here. Now we will be solving the same problem with h equal to 0.1. Clear? So your
Yeah, clear.
yeah. So first iteration is I equal to 1, right? So here first we need to find out K1. K1 is f of xi comma yi. That is first step is same f of 0 comma 0. K2 is f of xi plus h into K1. So h is 0.1 now, right? I of 0 is 0, 0 plus h is 0.1 into 2.5 equal to f of 0.1 comma 2.5 into this one is 0.25, right? So it is V by L minus 0.25 R by L. 2.5 minus 0.25 into 2 is 0.5. So it is K1 we have got, K2 we have got. So now we can find out Y of 0.1. Y of 0 plus H by 2, right? So it is 0.1 by 2. I of 0 is 0 plus 0.05 into 4.5. It is 0.225. This is the first step, right? Now we have to do again. Again, we will get next step, step 2. This was step 1, K1 now. Now for next step, K1 will be f of x1 comma y1, right? Or x2 comma y2 rather. So it, previous one was the first step. So f of x2 comma y2. x2 is 0.1 comma y of 0.1. 0.225. So it is 2.5 means V by L 0.225 into R by L. So it is 2.05. What will be K2? Can you tell me, Nasim? Just the expression you tell me. Hello?
Yes. It will be what it is. Okay, so it will be x2 plus h plus y0 plus h is k2 hk1.
It is x2 plus h comma y2 plus hk1, right?
hk1, yes.
So you tell me what is x2 now? x2 plus h is how much? Hello?
Yeah, x2 plus h is it is point two.
Point y2
Point
is
two.
how much?
Point two. Then comes y2. So it is
Not the sorry, this is not y2. Y1. This is also not x2. This is x1. So y1 is y of 0.1, that is 0.225, right? plus H is 0.1, K1 is 2.05. So this is how we calculate. 1 second. 0.25 plus 0.1. So this comes out to be 0.2, 0.43. So it is 2.5 minus 0.43 into 1 second, 1 second. Just a second. So K2 comes out to be 1.64. Okay. So now you have
Yeah,
K1
it's
and
1 point.
K2. You can find out Y of 0.2. Y of 0.1 plus H by 2. K1 is 2.05 and this is 1.6. Y of 0.1 is how much? 0.225. 0.05 into. So if we substitute this 3.69 into 0.05 plus 0.225.
It's point
So
four
you
zero nine.
Yeah, so your functional value using RK2 method and 2 steps, it comes out to be 0.4095. What was your true value? It was 0.4, right? 4120. So you can see it is more accurate here. Now, if you find out the error, basically 0.4095. This will be 0.0025 by 0.41.
Point
So
six zero
here,
six.
yeah, so your error here comes out to be around 0.61 percentage. So you can see here drastically the error has reduced. Previously it was for h equal to zero point 0.2, error was 2.91%. Now it is 0.61%. So now if you just one more thing we'll do here. If we can find the ratio of the errors. So here while taking the ratio of the errors, we'll not take the percentage error, we'll take the absolute error. That is, we'll not divide it, just the difference between the true value and the actual value. So this error was 0.012 here, and here it is 0.0025, right? 0.012 by 0.0025. So it is around, check, 0.01 is equal to 4.8. So now if we want to find out, uh, we say that any numerical method is accurate up to say O of h. Then we say O of h square, O of h cube. So we are saying here that the this method RK2 is accurate to say O of h power n, and we want to find out what is the value of n here. So how do we do that? What do we mean actually by it is the O of h square accurate? O of h square accurate means the ratio of the errors to the ratio of the step size is 2 here. If we take the log actually, then the ratio of the errors, log of ratio of the errors is equal to the ratio of the step sizes. So now if we just take here O of h power n, so one second, just a second. So this log of this ratio so this log of the ratio will be equal to one second, equal to 2. So if we want to find out one second, we're missing something here. So while you take this logarithm here, so this is always to the base of 2. So this is the actual, this thing you need to remember. So your ratio will be equal to 2 to the power n. So n log 2 will be 4.8. To find out n from here, you will get n approximately equal to 2.2. If you n is equal to 2.21, so from this we can say n is approximately equal to 2. So we can say that this RK2 method is accurate to O of h square. This is O of h square, which we were talking about. Is it clear?
Could you explain it once again, like ratio of errors? How
Yeah,
did you calculate?
actually, yeah.
Zero point zero
So what we
one
do
four.
is, can you mute yourself? The voice is echoing.
Okay, okay.
Yeah. So the thing is, we found out for two different step sizes, right? The error one and error two. Okay, I'll just write it here. So what we did here, first we had taken step size to be zero point 0.2. We found out our error that was 0.0001, and then we took h2 equals to 0.1. Just a second, I'll just come back. Okay, so so we first took a step size of 0.2, and we found out the error in that particular H1 was 0.0012. Then we reduced the step size and we saw that our error reduced to how much? 0.0025. So then what we did is we found out the ratio of the errors E1 by E2. This was equal to 4.8, right? So now we say that our method is accurate to O of h power n. We are saying here that the accuracy of our method is equal to O of h power n, right? So then how do we say that? What we mean actually? So if you find out E1 by E2 we found out, and H1 by H2 if you find out, that is 2, right? So by O of h power n we mean that E1 by E2 equals to Just a second. No. Just a second. I'll just clarify this one. Uh, so the thing is, E1 by E2 is 4.8, right? So what we mean is log of E1 by E2 by log of H1 by H2, that is equal to N. The order of the accuracy. N is known as the order of accuracy. That is, it is actually, if you see the expression for N, is log of E1 by E2 upon log of H1 by H2. So what we are basically trying to do here is, we are trying to see with the increase in or with the decrease in step size, what is the order of decrease in the error. Means suppose I have reduced my step size by 2 times, right? 0.2 to 0.1. So how is my error going to reduce? What is the order of reduction of my error? That we are trying to monitor here. So in that, any numerical technique, the order of accuracy will be given by O of h power n. This O of thing, this is called as big O notation. Okay. I'll write it here. In computer algorithm, there is this term called as big, don't need to understand that, big O notation. So from that, this O of h power n, we say O of h square, like that we say. So here we want to find out what is the order of accuracy of that method. So n is basically given by log of the error ratio E1 by E2 upon log of H1 by H2. So n is equal to log of 4.8 by log of 2. So if you find this out, how much we will get? Is my 1 second. No problem. Just a second. N is coming around 2.263. So we have to round it off to the nearest decimal, to the nearest whole number, because the order of accuracy cannot be in the order of, cannot be in decimal. So n is equal to 2. So that means we can say our RK2 method is accurate up to O of h square. Is it clear or more explanation is required?
This log is means a log to the base 2 or the natural log.
Anything you can do, because we are taking the ratio, no, it will not depend. ln also you can do log to the base 10.
Okay, okay, okay. Understood.
Because we are taking ratio of two logarithms, the base will not matter here.
Okay, okay.
Clear, right?
Yeah, it is clear.
So now we will move to the next topic. That is, we'll look into the Euler's method now. So now we will look into the Euler's method, the stability of Euler's method. Now we will look into. Before that, one thing I forgot to discuss here. So we had talked about this method also, right? Richardson's extrapolation. So we had talked about Richardson's extrapolation also, right? So what was Richardson's extrapolation? Basically, we found out the value of the integral numerically at two step sizes, one at h, one at h by 2. And then we suggested that a better approximation of the integral will be a combination of these two integrals. So our I knew was basically 4 times the integral obtained with step size h by 2 and divided by minus the integral by step size h divided by 3. So this was our equation. So here basically we did with 0.2 and 0.1, right? So we can apply this and see what is the error. So now if we see 4i of 0.1 minus I 0.2 by 3. So this if you calculate what was I of 0.1, I of 0.1, that is this one, right? 0.4095. 0.4095 and I of 0.2 was 0.4. So if you calculate this one, this will come around, just a second. Four into 0.4095 minus 0.4. So this is around 0.41267. So if you calculate the error here is 0.41267, 4120. Error if you calculate 0.4127, 4120, 5. So it is around 0.16%. So the error is further reduced here. You can see using the Richardson's extrapolation. Now, any doubts, any confusions, anything, Nasim? Or should I proceed?
But this formula isn't it for the trapezoidal rule?
Yeah, this can be used for anything. This integral you can evaluate using RK2, RK4 or using trapezoidal, anything.
No, the Richardson extrapolation, the formula you have written for IH2 minus IN upon 3. It's for trapezoidal rule, I think.
Yeah, I could not get you. What you are telling?
The formula you have used here in Richardson extrapolation, I'm saying, isn't it for the trapezoidal rule?
Yeah, okay, okay. You are saying it is for numerical integration, right?
Yeah.
No, yeah, that was I discussed it in numerical integration, but this is also applicable in case of your differential equations also.
Okay.
It is applicable here also. You can find out using the Euler's method. And that integral, that value of the function actually you can substitute here and you can find out a better approximation.
Okay, okay.
Okay. So now we'll move to the next topic, which is basically your stability analysis. So, so what do you mean by a stable solution? And what do you think these differential equations, the stability of the solution will depend on which parameter? So this accuracy or stability, whatever you talk about, all these things are dependent on only one parameter in the differential equation, that is your step size. And obviously the method which you are using to solve that particular differential equation, whether it is Euler's method or it is RK2 method or it is Runge-Kutta fourth order method, anything, there are two parameters only. First one is your step size and second one is the method which you are using. These two parameters only define your accuracy or the stability. So now here we are talking about the stability of a particular method, stability of Euler's method. So here the method we have fixed. What is the other parameter that we can change here now? That is only the step size. So you can understand for a particular method of solving the numerical differential equation, only parameter which will determine the stability or the accuracy of your solution is your step size. So your step size is very important here. Suppose you're given a particular differential equation, say anything like dy by dt equal to 1 minus 2y. Like that, any kind of differential equation you are given and you are asked to solve that equation using a particular value of step size. Say, I'll just give an example just for you to understand. Then we'll go into the method. Suppose dy by dt is given by 2y minus 1. And your initial value is given, y of 0 is 0. You are asked to find out, say, y of 5. Right? Y of 5 you are asked to find out. So then, suppose we take our initial value is 0, right? Then directly if we take h equal to 5, in one step we will get our solution, y of 5, right? If we take h as 1, then we have to do 5 steps, 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5. And we have already seen that the more lesser step size we use, our solution is more accurate. Now coming to the stability, is there any thumb rule like that? What value of h we should take to get a stable solution? No, there is no thumb rule here. So you cannot say that for a lower value of h your solution is accurate. Like accuracy, we can directly tell our solution is more accurate for a lower value of step size. But as far as the stability is concerned, we don't have an actual boundary, that is an adaptive, that is a optimum value of h we need to have for which our solution is stable. So here what we will do is we'll try to solve a differential equation. We'll not solve it directly. We'll see the answers I have just put it down and we'll see for different step sizes how is our solution changing. So just remember all these methods. We will be seeing in the last session, that is on 19th of October. One session I will take where I will do this, solve this and show you how in MATLAB we can show by plotting how your stability or your accuracy, how these are all varying. Okay. So now we'll be using the previous equation only. Okay. So what was our equation? Was equation was di by dt equal to v by L was how much? 2.5 minus 2.5. This was my equation, right? So first we will do Euler's method for h equal to 0.2. And we have to find out here I of 1. Okay. So your I of 0 is 0, and your for Eulers we need f of 0 comma I of 0. So that is 2.5. If we find out I of 0.25, it is I of 0 plus h f of 0 comma I of 0, right? I of 0 is 0, h is 0.25, this is 2.5, 0.6. Then next, again, if you find out I of 0.5, 0.75, like that, if you go on, if you find out I of 1 after 4 steps, you will get the solution as 1.172. So this you can see, if you find out 0.25, then 0.5, like this, if you go on, you will see that there is a continuous increase in the value of the function. There is a monotonically increasing function. There is no unstable thing, like there are no oscillations. The value of 0.25 is 0.625, 0.5 is increasing, 0.75, 1. Like that it is going on, like the value of the function. So this we can call a stable solution. Now if you do the same thing using h equal to 0.5, so if we take h equal to 0.5 and we'll solve the equation here, I of 0 is 0, f of 0 comma I of 0 is again same 2.5. Now I of 0.5 will be I of 0, f of 0 comma I of 0. So it is 0.5 into 2.5 is 1.25. Like this, if we go up to I of 2, we'll see here also, just a second, 2, 2.37. So here also, if you see I of 0.5, this is a stable solution because it is continuously increasing. Now, suppose if we take h equal to 1 and we try to do 4 steps here, I of 1, h equal, this we will get as 2.5. I of 2, if you do I of 1, h into f of 1 comma I of 1, this you will see it is coming as 0. I of 3, if you calculate, this will be again 2.5. Again, I of 4 will be 0. So here you can see I of 1, I of 0 was 0. Then your I of 1 is 2.5. I of 2 is 0. I of 3 is again 2.5. I of 4 is 0. So you can see here your solution is oscillating. That is, there is neither decrease nor increase in the continuous increase or decrease in the value. There is abrupt increase, decrease, decrease. Like that, solution is oscillating. So here we can say this is an unstable solution. So h equal to 1 is basically an oscillating or an unstable solution. Now we'll see with one more step size, say h equal to 1.5. Here if you do if you find out your I of 1.5, it will be some 3.75. The next step, if you see, minus 3.75. I of 4.5 is 11.25. I of 6 is minus 8. So you can see here that the function is again increasing, or it is abruptly increasing, like your solution is blowing up. That is, it increases. If you do 3-4 steps, you will see that it is enormously increasing. So again, this is an unstable solution. So for this particular differential equation, in Euler's method, any step size above 0.5, it is giving an unstable solution. So now how to find this boundary? That is, what is the value of the what is the optimum value of H, which basically decides your thing. So for this, we have another technique which is known as adaptive step size selection. Is this concept clear? What I'm trying to mean here?
Yeah, I understood.
Okay. So here, what we do is first, what is our I true here? From the numerical integration technique, we have seen this in our adaptive quadrature technique. It is in RK2 method, we can represent our true solution as your predicted solution plus C1 into H square. What is C1 into H square? That is basically the error term. Since our method is accurate up to O of H square, or your error is dependent on H square, that's why we are doing like this. I of H plus C1 H square. So suppose we take another value of H, which is H by 2. Your I true doesn't change, right? So we can write it as right. So if we subtract these equations, we'll get I of H minus I of H by 2 H square minus plus C1 H square by 2 equals to 0. So we can write C1 H square by 2 equal to I of H. Okay. This one, if we assume as delta, and this C1 by 2 as some other constant C, so we can write CH square equal to delta, right? Then again, what we do is with a different step size, H nu, we again do the same thing. The same operation, we do it with a different step size H nu. So then basically we will get another delta, which is delta nu. Clear? Now, we divide these two equations, delta by delta nu to CH square by CH nu square. So if we find out H nu from here, H under root delta nu by delta. So what is your delta nu now? If you know this delta nu, you can find out your H nu. So suppose we want this delta nu is your error, right? So if we say we want error of the order of say 0.005. So then for that, what step size we should use? Delta nu is basically your wanted error, means what is the order of the error you want. That if you fix a priori, you can find out your H nu. H nu will be here 0.0. So this is the adaptively we are trying to set our step size so that we can get a fixed amount of error and we do not get an unstable solution here. Is it clear?
Could you explain it once again?
Yeah, sure. So here what we are doing here is basically we want to find the value of the step size or the optimum value of the step size for which we get our desired error. Like and our solution is stable also. Like I showed you, for different step size, if we take a step size randomly, then we'll not get a stable solution. We might not get a stable solution. Just a second. So what we are doing here is we are trying to select a value of h, and adaptively we are trying to select the value of h, or how I can say you this one, that we are trying to select a value of h. We will fix our error a priori before doing the process. We'll fix our error, and we are saying that for this error order, what is the step size I should use? Okay, so this our RK2 method is accurate up to O of h square, right? Since it is accurate up to O of h square, we can write our solution as I true, that is the actual solution which is obtained analytically, that is equal to I of h plus C1 into h square. So then we can write it as I of h plus C1 h square. Now, if we do the same process using h by 2, we'll get I of h by 2 plus 2 times C1 h by 2 whole square. This we have discussed in the previous class, or one class before we have discussed this. So if we subtract these two, what we will get, our true value is same in both cases, right? So I of h minus I of h by 2 plus this thing C1 h square by 2 will be equal to 0. So from this, if we just simplify and manipulate some of the terms, we will get CH square equal to this delta. What is delta? Delta is I of h minus I of h by 2. Okay, up till this it is clear. So now this h nu is my new value of h, with which we want to get an error of delta nu. Your delta is basically the error, right? Or it's not the error actually. It is the difference between the integral at step size h and step size h by 2. The other way round of saying the same thing. So if we fix delta nu from previously, using this equation h nu equal to h into under root of delta nu by delta, and we fix delta nu from before only, then we can get this value of h nu. That is, this is the step size. 0.046 is the step size for getting an error of the order of 0.0005. Is it clear?
Yeah, understood.
Just we'll take a 5 minutes break and then I'll come back.
Okay, sure.
Okay, so we'll start the next topic. Okay, so now we will see one more numerical solving the numerical ODE technique, which is known as the predictor corrector technique. So till now we have seen that the most accurate method is the RK4 method, right? So here we will be using two-step. It is a two-step method, and first step will be predicting our solution. Then in the second step we will try to we'll be trying to correct that equation. And then we'll try to see what is the error order. So this predictor corrector method, actually the order of error is very less here. So in predictor corrector method, what we do is, so this is an actually an implicit technique for solving this nonlinear differential equation. So till now what we have studied is actually explicit techniques, the Euler's method and all. These are all explicit techniques. So directly we are getting the solution in one step. But here what we will do is first step will be predicting the equation and next step will be trying to correct the equation. So now we'll look into the the first order, the first order predictor corrector method. So here first step we'll be using the Euler's explicit technique to so first we will be using Euler's explicit technique to estimate the solution. So this is called the predictor step. We write it as P. So yn plus 1 predicted is equal to, using Euler's, this is normal thing, h into f of yn. This is explicit Euler's technique, and this is not accurate. The order of accuracy is less. So this is not your answer. So what we used to do in the previous techniques, in Euler's technique, this was our final answer of yn plus 1. But here what we do is, next step we will be correcting this solution. How we will be correcting this solution? We correct the estimate, correct the estimate We'll correct the estimate by using an implicit technique. So what implicit technique we'll use? We can use the trapezoidal rule for the initial value problem. What is that? So this is my corrected step, right? And this is my final answer. Yn plus 1 corrected is equal to Yn plus h by 2 f of Yn f of Yn plus 1 predicted. So this is the predictor step. Just highlight this one. First, we will predict this. Next step, we will try to correct. Using these two steps, we will see using an example here that our predictor corrector method is more accurate compared to your the explicit techniques. Is it clear?
Yeah, it is clear.
Okay. So now we will see one problem and we'll try to understand. So the question is apply first order so your differential equation is dy by dt. Just simple equation we are taking equals to 5y. Y of 0 equals to 1. We have to find out y of 0.05. And h is given as 0.05. Just one step we'll be doing. So now, first we'll try to solve it analytically. Okay. So it is basically dy by dt equals to 5y. So we bring this 5y here equals to dt. If we integrate both sides, we'll get 0.2 ln y so equals to t plus c. So we will get y equals to, okay. So first we'll substitute the initial condition, right? Y of 0 is 1. So 0.2 ln y. So ln 1 is 0. So c will be 0, right? Therefore, e equal to 0.2 ln y. Y equal to, so this is your solution. Y equals to e to the power 5t, right? Based on the initial condition. So now what is my exact solution? Y of 0.05 is e to the power 5 into 0.05. So this is my exact solution, 1.2840. Just a second. So my exact solution here is 1.2840, right? Now we'll try to see how we can solve it using our predictor corrector method. Now, clear up to this, right?
Yeah, it is clear.
So Yn plus 1 predicted is equal to Yn plus h f of Yn. So y1, that is 1, y of 0, h is 0.05, f of y1 predicted, y of 0 is 1, 0.05, y of 0, f of y is 0, right? F is, how much is f here? 5y. So that is 5. So y1 predicted is 0.25. Sorry, 1.25. So you can see the true solution was 1.284, right? And your predicted solution is 1.25. So it is near the true solution, but error is there. What is the order of the error? So it is basically y true minus y of predicted. Just absolute error if we find out, or percentage if we find out, y true percentage of error is 2.65%. So we want to make it more accurate. So what we do is we use another implicit technique here. So now we will see what we can do using the corrector. This next step is the corrector step, right? So yn plus 1 corrected is equal to yn, that is y0 plus h by 2 f of yn, f of y1 predicted. Y0 is 1 plus 0.05 by 2, f of y0 is 1 plus f of 1.2. F of 1 is 5y, right? So it is 5,
5.
5 plus 6.25, right? So this, if you calculate, how much it will come? Okay. 11.25 into 0.055. So it is 1.2815. What was your true solution? 1.2840. And your predicted was how much? 1.2. So you can see here that your corrected solution, that is the y1 corrected, is much more accurate compared to the y predicted. It is much more nearer to your true solution. So what is your error in corrected method? Is 1.2840, 8125 by 1.2. So here your error, if you calculate, is only 0.22%. So did you get this thing? Why we are doing these two steps, one for predictor and one for corrected method?
Yeah, first we are means predicting it, then we are that correcting our numerical value.
Clear, right?
Yeah, it is clear.
Okay. Uh, this was the first order predictor correct. So here what we can do is, if we want to further reduce the error, we can do one more step or multiple steps of this corrected technique. Like if we do the second step of this corrected technique, what will be yn plus h by 2 f of yn plus, here we were using the predicted method, predicted solution, right? So here we can use the new corrector solution. So if you calculate this, 1.281. So if you calculate here, it will be much more error free. So here, if you find the error, it will be around 0.09%. So if you continue like this, 4 more steps of this corrector step, you will see that error will reduce at a much faster rate. And this all these. So basically, what we are doing here, we are using a mix of explicit and implicit technique. And in that way, we are trying to reduce the error. So uh, the only objective here is to reduce the error. That's why we are trying to develop more and more techniques at much less computational effort if we can. Clear?
Yeah, clear.
So this was the first order predictor corrector method. So now we will see the fourth. Just I'll write the equations for fourth order predictor corrector. So the equations here are a bit of complex. Yn plus 1 predicted is equal to Yn 55 times f of Yn minus 59 times f of Yn minus minus 59 times f of Yn minus 1 plus 37 times f of Yn minus 2 minus 9 times f of Yn. So these f of Yn plus 1, all these are the slopes. And these coefficients, whatever we are seeing, 55 minus 59, 37, all these are all these are the weighted averages. So this is the predictor method. And the corrector equation is Yn plus 1 corrected equals to Yn 9 times f of Yn plus 1 predictor plus f of Yn minus 5 f of Yn minus 1. So these are the equations for your fourth order predictor corrector method. So this is a bit complex to remember. You can just take one random differential equation and you can solve it using this fourth order predictor corrector method. And you can see here the order of error will be further less than compared to the first order equation.
What is y n minus 1 here? Means the n minus 1, n minus 2.
Why, one second. Hmm. To look into it once. I'll just check and I'll get back to you in the next class. Okay.
Okay, sure.
So now a small topic is remaining, which is the stability analysis. Will to determine our aim will be here to determine whether an algorithm is stable or not. A general we looked into the stability of our Euler's method, right? And how we can find out an optimum value of h. So that and all we look. But now we will be seeing any random algorithm if you give any random iterative technique is presented, iterative formula is given to you, and you are asked whether that tree is stable or not. So how you can do that? So we will be looking into that now. Stability analysis. So what is our aim here? Our aim is to determine whether a given algorithm to solve an ODE so we can tell here that our explicit methods like Euler's explicit method, or it can be unstable. If we do not choose our H properly, then our Euler's method can be unstable. The implicit methods, these implicit methods are more stable. So now, what do we mean by the stability and the instability? This thing. So, in what way can our solution become unstable? So, there are basically two ways. One is known as spurious solution. The solution which we get by these techniques, it is not at all true. And the second way by which our solution can get inaccurate or unstable is the numerical error, right? So this numerical error is very this thing is actually uh, inbuilt in any numerical technique. So with each iteration or with each step, that keeps accumulating. So this new there are two types of things. So the solution, so there are two types of solutions. One is the spurious solution, and other is the numerical error. So these are the two ways in which our solution of an ODE can become inaccurate. We'll look into what is the difference between both these things. What is a spurious solution? What is numerical error solution? We'll look into that. So now let us consider a form of a general ODE. So let us consider a general form of an ODE solver algorithm. First, I'll write down and then I'll explain. Okay. So first, these are the this yn plus one. We can write it in terms of the coefficients, which is alpha naught yn plus one, alpha one yn, alpha two yn minus one. Like this, we can have up to three steps. We can have a k terms, and we can write it like this. Next, we will have our different this derivative term, which are yn minus yn plus one dash. So this is the general form of an ODE solver algorithm. Many of these coefficients can be zero, right? So we don't need to care about that, but this is the general form of the equation. So now let us apply this equation to a. So this is a like a theoretical process. You just tell me if you have any doubt anywhere.
Okay, sure.
Any step you miss, you can tell me. Okay.
Okay.
So we'll be using this equation to our general simple ODE. So in most of the cases, this alpha naught coefficient, this will be zero. If you see any technique, say our Euler's technique or any technique, if you see this alpha naught coefficient, that is the coefficient of yn plus one, that is mostly zero because we don't have any terms on the right hand side of yn plus one. Yn plus one is always on the left hand side. So say 0 for most techniques. So then we can write it as yn plus 1 equals to alpha 1 yn, alpha 2 yn minus 1, like this up to alpha k. Perfect. Just a second, power has gone. 1 second. Okay, so are you able to listen to me, Nasim?
Yeah. And visible.
Okay, so these are the terms, and this here you can see yn plus 1 dash, yn dash we have. So yn dash is basically the derivative, right? So derivative is given by lambda into y. So yn plus 1 dash, we can write it as lambda yn plus 1, right? Like that we can continue lambda yn. Just a second. So power is not there. Okay, we'll stop the class today. We'll continue in the next class. Okay.
Yeah, sure. No issue.
Because actually power has gone. I can't continue now.
Okay, sure.
Okay. So actually next class, not in next Saturday. So I will take it in day
This
after tomorrow. That is Monday only. That
on
is on
Monday.
this Monday, 7th.
Yeah, I understood.
Yeah, from same time, 7 o'clock. Okay.
Okay, sure.
Okay. Thank you. Bye.
Okay, thank you. Bye.